Okay, this is a continuation of Chapter 4, Section 2, Exponential Functions, Part B. So we're going to extend this concept of an exponential function to from simple interest to compound interest. So recall that the formula for simple interest, I is your interest earned and P is the principal. The principal meaning the amount you invested, put in for investment. R is the interest rate. Now that's usually given in percentages, and of course we always take that down to an actual number by dividing by 100. And T is our time. And that's usually given in years. So that's our formula on how much interest we get earned. We earn after 1 year or after however many years is indicated by T. So suppose you invest an amount of money and you don't spend the interest. So if you don't spend the interest at the end of the time, let's say at the end of a year, it's added by the financial institution to your principal after that year. So your new principal is given by your original principal P plus P times R. Why is it P times R? Because this is after 1 year, and so our T is equal to 1. So that's the original amount invested plus the amount of interest earned in 1 year. So that means equation 2, if I pull out the common factor in P plus P times R, I get P times 1 plus R. And that's the amount we have after 1 year. Now if this new amount is left in the institution earning interest for another year, the new principal is given by the interest rate earned after year 2 plus the principal after year 1, or the account amount, the interest, that should say interest amount after year 2, maybe it is supposed to be account, after year 2 is your new principal after year 1 plus year 2 interest earned. So it should be the amount in your account because it's your new principal after the first year plus year 2 interest earned, which is given by P times 1 plus R. We get that from right here, plus this is my new principal times my rate times my time. And what I'm going to do, since our time is again just 1 more year, then we get this part of the equation. My T vanishes because it's times 1. And what I do for right here is notice P times 1 plus R plus P times 1 plus R times R. The common factor here is P times 1 plus R. So when I pull out the common factor, I get P times 1 plus R times 1 plus R, which is equal to P times 1 plus R squared. And if we continue on in this fashion, it's not hard to show that the formula for the account balance A, after T years at a fixed interest rate, is given by A is equal to P times 1 plus R raised to the T. So we're going to generalize this formula. So what we're going to do, and what happens here, is we make it more abstract and we develop a formula. So for right now, we're just going to take the formula for granted, and in a later lecture I will tell you, if I remember, how we derive it for those who care. So if P dollars are deposited in an account paying an annual fixed rate of interest, R, That's a bad typo. That should be compounded n times a year. Then after t years, the account will contain a dollars given by the formula, and this is the formula. A is equal to P. Now here is our base. Notice this is in parentheses. 1 plus the rate divided by the number of times it's compounded per year, raised to the t times n. So this is an exponential function of the variable t. So the number n is given, it's fixed. The rate is fixed, and we can compute it using the variable of t. How much will I have after 20 years? T is equal to 20, etc. So from here on out, calculator use is okay. So this is really, I made this for my students in class. You all can use online calculators or calculators on your phone. You shouldn't use a graphing calculator, but you know, how am I going to know? So I'm just going to not worry about for this class. So it should have at least the following buttons: 10 raised to the x, and underneath log of x, just log, e raised to the x, ln, y raised to the x, the x root of y. So those are the buttons in some combination. For example, my calculator right here has x raised to the y, and I don't even see an nth root of x. There's my log, and there's my ln function. I can do 10 to the x by using this function. There's my e, so I can do e to the x. So what I'm not seeing is the nth root of x, but that's okay. I can always download a better calculator if I need it. I don't think I need it. So let's do this example. So we're going to suppose that $1,000 is deposited in an account paying 4% interest per year, compounded quarterly. That's just financial speak for meaning it's compounded 4 times a year. So find the following. Find the amount in the account after 10 years with no withdrawals. And B, how much interest is earned over the 10-year period. And here's a formula you will use. Use interest earned is equal amount in the bank after 10 years minus original amount. So let's go ahead and do that. So our guiding equation is going to be A is equal to P. Now here comes the base. It's 1 plus R divided by N raised to N times T. So you could actually write this as a function of T. F of T is equal to P times 1 plus R divided by N times N times T. The only thing here is our output value, F of T, actually equals our amount. So let's write down our givens. So our principal is equal to 1,000. Our interest is 4%. So our rate is our interest rate is 4. And you should change that into either a decimal or divide it by 100. If you divide it by 100 here, it's kind of nice to go ahead and simplify it. So that's 1 in 25. The number of times, n, is equal to 4. And our value of t is equal to 10 years, right? 10 years. 10 years. So years. So let's find it. A is equal to 1,000 times 1 plus my rate, which is 1 divided by 25, over my value of n, which is 4, raised times n, 4, and t is 10. So let's go ahead and simplify this. So we're going to use PEMDAS, and PEMDAS insists that we find out what is in parentheses first. Clearly my exponent is going to be 4 times 10 is to the 40. So we have to figure out what is 1 plus 125 divided by 4. So let's go ahead and do that, but not that way. So let's move up here. So let's rewrite this as 125 divided by 4. And you can put that 4 over 1. Well, I would really like to change this into a multiplication problem. And I can. I just did. I just wrote multiplication there rather than division. But the price I have to pay is I have to invert the 4 divided by 1. That becomes 1 divided by 4. So that is equal to those. So in other words, I have to write, instead of 4 divided by 1, it's reciprocal, which is 1 divided by 4. So this is 1, and 25 times 4 is 100. So now we have to figure out, so this is 1 plus 1 over 100. So let's go ahead and take the next step. My amount is going to be 1,000. And what is 1 divided by 100? Well, I'm going to write 1 is 100 over 100 plus 1 over 100 raised to the 40th. And now I have A is equal to, and this is 101 divided by 100 raised to the 40th power. So now PEMDAS says, we're going to get out our calculator to do the rest, that we do this next. But I want to note that my base is greater than 1. So my base is greater than 1, so this is an exponentially increasing function. So let's go ahead and do it. I'll show you how to do it with a calculator, just in case some of you, I've not really been allowing you to do the calculators. So I'm going to bring up my calculator, and the first thing I'm going to do, for me, I'm going to be using x to the y. So my x is going to be 101 divided by 100 equals x to the y, 40. So that's my result. So that's the result of doing the operations right here with the red. And then I'm going to multiply that times 1,000. So my amount is going to be $1,488.86. So my amount is equal to $1,488.86. So the question also asked, the second part, how much interest is earned over the 10-year period? So interest earned is equal to my final amount, because I'm not spending any of this, okay? Minus original amount. I'm not going to write amount, which is equal to 1,488.86, and I invested $1,000. That's really easy to do. We certainly don't need a calculator for that to calculate its $488.86 in interest. That's just letting your money make money, which seems kind of weird that that could even be a thing. So let's do another problem. So again, we're going to use the same more or less type of formula, but this has two parts. So Becky must pay a lump sum of $6,000 in 5 years. So what amount deposited today at a fixed rate of 3.1%, compounded annually, that's once a year, will give a final amount after 5 years, a final amount of $6,000 after 5 years. That's worded rather badly. So the fixed rate is 3.1%. So let's do this. So again, my guiding equation is A is equal to P times 1 plus my interest rate over N raised to the N times T. So what amount deposited today? So our variable P is our unknown. Our rate, which is fixed, is 3.1%. Now if you want, if you're okay with doing this, you can either write that as 3.1 divided by 100, or simply move the decimal 2 places to the right to get 0.031. So here it is, 3.1. That's one place. I have to add a 0 to move another. Then I put the leading 0. It doesn't matter. It's compounded annually. That's kind of nice. Our t is equal to 1. And our total time, our t is equal not to 1. What I meant to write there is our number of times. Our n value is equal to 1, and our t value is equal to 5. So the final amount that she wants to get is $6,000. So let's put everything in. My amount is $6,000. My value of p is my unknown. 1 plus my rate divided by n. So I'm just going to write it as 0.031 divided by n is equal to 1 raised to the 1 times 5. So let's solve this equation. Remember, we're solving it for p. So this is 6,000 is equal to p times 1 plus 0.031 is 1.031 raised to the 5th. So now it's time to get out our trusty calculator, and we're going to calculate this value right here. Why PEMDAS? Because we did PEMDAS here, we simplified what's in parentheses, and now our next thing is to do exponents. So again, we get our trusty calculator, and my value is 1.031, and that's going to be raised to the 5th. And my answer is 6,000 is equal to P times my calculator amount, which is 1.649. I'm just going to put it right there, 1.649. So now all I have to do is solve for p. So I need to divide both sides by 1.649, and that will get me my principal. Now in my calculator, I hope I didn't mess that up by hitting that button again. I'm just going to go ahead and do a little algebraic trick. I'm going to divide it by 6,000. And that's not going to be the right answer because I'm supposed to be dividing 6,000 by this number. But I'm going to do it anyway. And then see right here where it says x to the minus 1, or sometimes your calculator might have 1 over x. I'm going to hit that value and hit equals. And that gives me the answer, what was it? Of $5,150.60 is the principal I have to invest. That's my principal investment if I want a return of $6,000. You know, a 3.1% interest rate is nearly unheard of. You're not going to get that. But if you did have an opportunity to do that, you could literally increase your investment by that much. And we're using calculators, so I'm going to go ahead and subtract 6,000 from it. And then we're going to take its absolute value, a malformed expression. You get almost $850 earned in interest in 5 years. Not bad. So what was our second question we were asked? If only $5,000 is available to deposit now, what annual fixed interest rate R is necessary for a final amount of $6,000 after 5 years? So now we literally use the same technique, except in this case, our unknown is R. Our R is our unknown. Our final amount, again, we want to have $6,000. Our principal that we have to invest is fixed. It's more like it. In real life, I have $5,000. My n value is equal to 1, and my t value is still equal to 5. So let's plug it in and see what we get. So my A is equal to 6,000. My P is 5,000. 1 plus R is my unknown, and R is divided by 1. 1 plus R raised to the T. That's supposed to have another 0 in there. That's 5,000. So this is 5,000 times an amount. So what I'm going to do is I'm going to divide both sides by 5,000. And that's equal to 1 plus R is my base raised to the T. And I should have put right there that my T is actually known. It's 5 right here. So let's simplify this. When you have trailing zeros and you're dividing, you can just tack them off right there. So I get 6 divided by 5 is equal to 1 plus R to the 5th. So how do we solve this? Because our unknown is locked up in here. So what we do is we raise both sides to the value to the 1/5. Or we take the 5th root. It's the same thing. So that gives me 6 divided by 5 raised to the 1/5 is equal to 1 plus r raised to the 5th raised to the 1/5 is 1 plus r raised to the, I multiply these exponents, and 5 times 1/5 is 1 plus r. So r is equal to 6/5 raised to the 1/5 power minus 1. And that's equal to r. Now notice this answer is exact, but that doesn't really help me. I want a numerical value. So I have to know how to raise 6/5 to the 1/5. So we get out our calculator. We clear everything. 6 divided by 5 equals, notice it's going to be greater than 1. And I'm going to raise it to the value of 1 divided by 5. Now I'm going to hit equal. And then I'm going to subtract. So this value right here, 6/5 raised to the 1/5, is 1.037. And then to get my r value, I'm going to subtract 1. So my answer is that r is equal to 0.0371. But this is not a percentage. So to convert to a percent, multiply by 100. So what I like to tell students is a percent is not a number. If I'm going to use a percent in a formula, I have to convert it into a number. So I have to divide the percent by 100. And then you're given a number. And then you want to convert it back to a percent. And multiplying by 100 is the same as moving the decimal 2 places. So it's 3.71%. And that makes sense. If you think about what we just did, that makes a lot of sense, because at 3.1%, we had to invest $5,150.60. If I can only invest $5,000 and I want the same amount, then the interest rate changes and it has to go up, and it does. It goes up by a little bit from 3.1% to 3.7%. And you certainly won't find any banknotes that pay that much unless you're really, really lucky, or you know something about finances that I don't. And that's pretty easy, to be honest with you. So let's go back and continue down the path. So here we have a new mathematical constant. It's one of the most interesting and important constants, far more important than pi. And this mathematical constant is Eulers Constant, and it's irrational like pi is irrational. So we're going to consider the formula a is equal to 1 plus r over n raised to the nth power. Why are we going to do that? Because that's the formula we're considering. So notice that a is an exponential function in the variable n. This is what makes it weird. The variable n is included in the base value, and it is also included in the exponent. So it's a little bit different from what we were doing earlier. So suppose we wish to calculate how much more money we get if we compound more and more times per year. Twice a year, 3 times a year, 1,000 times a year. This is the same as asking the question, what happens to our function a of n as n approaches infinity? Now, since we're going to be adding 1 to a fraction, and these numbers r and n are both going to be greater than 0, the base is always going to be greater than 1. So this is an exponential increasing function. And what we're literally trying to do is, since we're finding out what happens as n goes to 100, what happens to a to the n, this is the exact same question is trying to find the horizontal asymptote of a to the n. Now, the amazing answer to this question is that actually a horizontal, not an oblique, but a horizontal asymptote exists. And the value of that function as n approaches to 0 is y is equal to 2.718218828. It's Eulers Constant. Now, this is just an approximation. Eulers Constant is irrational. This decimal expansion would go on forever and ever and ever and never repeat. How we know it would never repeat is a very interesting question, but I'll tell you this. The Greeks did not know about the decimal expressions of numbers, but they sure as heck knew that the square root of 2 was irrational. And of course they couldn't say, well, the decimal expansion never repeats because they didn't use decimal expansions. But if anyone's interested about that, let me know, and I will show you how we know that the square root of 2 is irrational and it never repeats. So here we have another formula. If $P are deposited at a rate of interest R, compounded continuously for T years, then the amount A in dollars at a fixed rate R in time T in years is given. A is equal to P times E. So our base is a constant now. It's Euler's constant. E raised to the R times T. Or if you want to look at function notation, it's the same as f of t, or f of t, is equal to e to the rt whenever p is greater than 1. So let's use that formula to actually calculate the problem. So our formula for continuous compounding is A is equal to P times E, which is Euler's constant, raised to the RT. Now, this may be confusing to you, so I'm going to rewrite it over here. A is my amount, P is my principal, and it's multiplied times E, which is my base, raised to the RT. That's the important thing, is you realize the base of this exponential function, the base is Euler's E. And I give you the if you wanted to, you could write it Ft is equal to P times my base E, that's a constant, times R times T. So let's use that. So suppose $500 is deposited in account. So my principal is, I said 500, I meant to say 5,000. My rate is 3 divided by 100. We always have to convert a percentage into a number. And you can do either 3 divided by 100, so that's tenths, that's 100ths, that's 3 100ths. Either way. And my time T is 5. The word compounded continuously is what clues you in to using this formula. So let's calculate it. So A is equal to 5,000 times e raised to 0.03 times 5. So again, we're going to do this part first. Remember PEMDAS, parentheses, exponentiation, multiplication, division in the order they occur going from left to right, addition, and subtraction in the order that they occur going from left to right. So what we have to do is find this value, e raised to the 0.03 times 5. So let's do it with my calculator. So I'm going to clear it. If you see right here, I have my e. I'm going to write my e, and it knows what the value is. And it's going to be raised to the y value, and the y is 0.03 times 5. Now I'm going to hit equals, and then I'm going to multiply. So that's what this amount here in parentheses is 1.161834243, and then I'm going to multiply it by 5,000, and I get $5,809.17. Not so bad. So getting back to our lecture notes. So exponential functions are often used in models. Last year I was doing this lecture during the first of COVID-19, and I took the opportunity to explain exponential models and how to look at them and why COVID-19 was an exponential model. If you're curious, it's just a little bitty video all by itself, and I will make it available to you. You won't be tested on it or anything like that. And remember, COVID-19, only part of the model is exponential. There's other braking factors as well, but the engine, one of the main engines, is an exponential model. So here we have the general form of an exponential model as a function. Again, the function, the independent variable is t, which is time, usually in years. Y naught is usually interpreted to be the amount or number present at the very beginning, at t is equal to 0. And hence corresponds to the point on the graph ty, which is equal to 0, f of 0, which is equal to 0 times y naught. Because f of 0, e to the 0 times t is e to the 0, and e to the 0 is 1. So this is the 0 y naught, which is a constant. So here we go. So we're given, bring this one up here, all kinds of things in nature, as it turns out, are modeled by exponential decay and increase. So if the base is greater than 1, then it's increase. If the base is greater than less than 1, it's decrease. So exponential increase and decrease. Things that self-replicate, like viruses or fires, or rabbits let to breed and reproduce without bound, increases exponentially. So we're given our base function, f of t, is equal to 0. Yeah, we're absolutely going to be using a calculator here. There is no reason, and to be honest with you, this is a real life model. So e is a constant, it's not a variable. That's the reason I wrote it in yellow. Now look at that, raised to the 0.00609 raised to the t. And remember, you're comparing this to f of t is equal to y naught times e to the k t. So in this case, my y naught is equal to this amount right here, 0.001942, and my k value is equal to 0.00609. But all we need to do here is, let's read the whole entire problem. Let f of t be this function. I'm not going to try to say that in words. Model the amount of carbon dioxide in the atmosphere in parts per million, where the domain of the function, in this case values of t, is in the range between 1990 and 2275. So find the amount of carbon dioxide in the atmosphere in parts per million, modeled by the equation at t is equal to 1990, and again at t is equal to 2020. You will need to use a calculator. So literally all we're asked here is to find the value of f of 1990 and f of 2020. So this is going to be 0.001942 times e raised to the 0.00609. And what is my value of t? 1990. And down here, this is the same, ditto, ditto, e, ditto, ditto, but we're raising it to the power of 2020. So let's go ahead and do this, again with a calculator. So the first thing I want to find here is e raised to 0.00609 times 1990. And this value right here is the value of the exponential part, the e raised to that. But now I have to multiply it times the start value, the k, the y naught value, and that's 0.001942. And the answer we get is, for this one, f of 1990 is equal to 356.047. We'll just do 356.04, I think maybe round it up, parts per million. Now I'm going to let you do this one. It's the same approach. You just plug in the value of 2020 here, and I'm going to give you the result. F of 2020 turns out to be 426.87 parts per million. Oftentimes parts per million is abbreviated ppm. And if you wanted to see that function, you could go to GeoGebra. They have a drop-down menu where you can choose the constant e as your base. Just remember, I guess the point here that I'm anticipating is you might think that e is a variable, but e is a constant. E is a constant. And if you don't have a calculator that has e, You saw the value I gave you there, you can use that value. You want your calculator to have E, and in all likelihood it will. If it has the buttons that I just told you it should have, then it will work. So that's actually it for Part B of Section 4.2.